This presentation covers Chapter 1, Sampling and Data. The first chapter of your textbook sets the stage and gives you basic terms that you'll use throughout the course to complete business statistics analyses. 1.1 talks about the definitions of statistics, probability, and key terms in an introductory statistics course. Statistics is the science of collecting, organizing, analyzing, and interpreting data in order to make decisions. So in business, we make business decisions all the time, from deciding, if you're a shoe manufacturer, what shoes to produce for a certain market. For example, basketball shoes, tennis shoes, shoes for casual wear. There are all sorts of decisions that need to be made in terms of how many shoes to produce, where to market them, who's buying the shoes, what color of shoes we should produce, and statistical analysis helps us in business to make these types of decisions. Descriptive statistics is where you will learn how to organize and summarize data. So organizing and summarizing data is called descriptive statistics. And what you can see here with these graphics are two different graphics representing how descriptive statistics works. So for example, without descriptive statistics, all we would have would be like a big spreadsheet full of data, full of numbers that maybe wouldn't make sense at a glance. Descriptive statistics allow us to take that information and make it readable for most people. For example, on the left chart here, we see that it is our student status of students that are full-time and part-time at two different colleges. And it's pretty easy to see that there are more part-time students at De Anza College versus Foothill College, for example, percentage-wise, and also the total number. On the pie chart to the right, you can see that it's pretty easy to see that most of the statistics students are freshmen. Inferential statistics. So after you have studied probability and probability distributions, you'll use formal methods for drawing conclusions from good data. The formal methods that we call this are called inferential statistics. Think about infer or deduce. That's where the inferential statistics comes in handy. We're able to use those statistics to help us make decisions. So the goal of statistics isn't just to perform all of these calculations using formulas. That's fine and dandy if math is your thing. But in business statistics, most of us are interested in getting results out of those calculations. So the calculations can be done using a computer. You can do them by hand. You can use a calculator. There's all kinds of ways to do it. So the understanding of what the information is the most important thing in business statistics. So if you can thoroughly grasp the basics of statistics, you can be more confident in the decisions that you make in business and in life. Probability is the mathematical tool used to study randomness. It deals with the chance or the likelihood of an event occurring. For example, if you toss a fair coin 4 times, the outcomes may not be 2 heads and 2 tails. So for example, if I have a coin and I flip it 4 times, there's a chance that it might be all heads or it might be all tails because I've only flipped it 4 times. If I flip it 4,000 times, however, the outcomes will be close to half heads and half tails. If you're ever curious and want to test this for yourself, go ahead and flip a coin 100 to 200 times and log each time if it was heads or tails. And then by using statistics, you can calculate that and determine that it probably is, even with 100 to 200 times, for example, flipping that coin, it's probably going to be close to 50-50 in terms of probability of getting heads or tails. So it's a neat little test if you want to try it out yourself, if you have some spare time. So statistics is based on the theory of probability. The theory of probability has been around for a very long time, and it was used, at least initially, to determine what the level of probabilities were for a winning hand in a game of chance, such as poker or blackjack. Predictions take the form of probabilities. So, for example, the likelihood of an earthquake happening. If it's going to rain outside, what your course grade might be in this course. Like, for example, what would be the probability that you would get an A out of this course? We could look at historical data from previous courses, for example, to give a problem, the likelihood of the average student, what would their grade be? Also, in a real world setting, vaccinations causing the disease that it was designed to prevent. There's a probability for that. Or more likely, what we would look at probabilities with vaccinations would be what are the likelihood that somebody will have an adverse reaction. For example, anytime that there is a vaccination given, there is a small risk that somebody's going to have an adverse reaction, like that they may contract the disease, or that they might have bad side effects. And by using statistics, we can say, for example, out of every 1 million people that get the vaccine, there might be 4 or 5 people who die from it, for example. And there is a statistic for that. Hopefully it doesn't happen to any of us if we get a vaccination, but it could, a very small likelihood, but there is a probability that it could happen. When we start looking at statistics, one of the terms that gets kicked around a lot is the population. In statistics, we generally want to study this population. You can think of a population as a collection of persons, things, or objects under study. For example, if I want to study the eating habits of your average college student, the population would be college students. So if I determine the population, we want to know the average mean amount of money first-year college students spend at San Jacinto College on school supplies that do not include books. So to do this, we randomly survey 100 first-year students at the college. 3 of those students spent $150, $200, and $225 respectively. So if I'm looking at the population, if I'm going to determine that, what we would see here is that the population is all first-year students attending the college this term. Okay. Now, we have our population, but the issue is the population sometimes can be, depending on the size of the population, can be difficult to study as a whole. Instead of studying, say, all first-year students at San Jacinto College, we would look at a certain sample size, okay, because it's easier to pull a smaller number of people than the overall population, and the sample then would be our that portion of the larger population, and we can study that portion, the sample, to gain information about the population. So to determine the sample, we want to know the average amount of money, again, first-year college students spend at San Jacinto College on school supplies that don't include books. We randomly survey 100 first-year students at the college. 3 of those students spend $150, $200, and $225 respectively. So if I'm looking at the sample here, your sample would be your 100 first-year students at the college. It could be all students enrolled in one section of a beginning statistics course, for example. That might be a small sample of the first-year students at the college. The parameter is a number that is a property of the population. Because it takes a lot of time and money to examine an entire population, sampling is a very practical technique. What you'll find is that the larger the overall population is, the more expensive and time-consuming it's going to be to contact everybody, have a survey, for example, for them to fill out, and then process all of those surveys. It can take a very long time. It can be incredibly expensive, and because of that, we typically pull a sample of the population. Okay, so we're going to determine the parameter. I'm not going to keep repeating the the San Jacinto College statement over and over again. So now we're looking at the parameter. The parameter is the mean or the average amount of money spent by first-year college students this term. Okay? That is the thing that we're looking at. That's what we want to know, is what is that parameter? It's the average mean amount of money spent. Our statistic is a number that represents a property of the sample. For example, if we want to consider one math class to be a sample of the population of all math classes, then the average number of points earned by students in that one math class at the end of the term is an example of a statistic. So if we're going to determine the statistic for our school supply example here, here's how we would do it. The statistic is the average amount of money spent by first-year college students. That's what we're looking for. Okay, that's the statistic that we are going to, by our research here, that's what we're going to find with our survey. Okay. Variables. A variable, and it's notated by capital letters such as X and Y, is a characteristic of interest for each person or thing in a population. Typically, if we want to determine the variables in this example that we had for San Jacinto, our variables could be the amount of money spent by one first-year student. So that would be X. The money amount is spent by one first-year student. Now, variables can either be numerical or categorical. Okay? Numerical variables take on values with equal units, such as weight in pounds, times in hours. They are numerical, they're numbers. Categorical variables place the person or thing into a category. If we let X equal the number of points earned by one math student at the end of the term, then X is a numerical variable. We could let Y be a person's party affiliation. Then some examples of Y include Republican, Democrat, and Independent. Y would be a categorical variable. Another categorical variable might be the model, make or model of a car, for example. If somebody drives a Toyota or a Ford, those would be categorical variables, for example. Data are the actual values of the variable. They may be numbers, they could be words, they could be a mix of both. And occasionally you hear the word datum. All that datum is just a single value. Data is more than one value. So let's say we want to determine the data from our example here. The data are the dollar amounts spent by the first-year students. Examples of the data, as you can see above here, are 150, 200, and 225. Let's talk about data, sampling, and variation in data and sampling. So you have two main types of data. Data, it might come from a population or from a sample. Okay. Small letters like X or Y generally are used to represent data values. Most data can be put into following categories: qualitative data and quantitative data. Qualitative data are the result of categorizing or describing attributes of a population. For example, hair color, blood type, ethnic group, the type of car a person drives, and the street a person lives on are examples of qualitative data. You'll see that they are describing a characteristic of the population. For example, if I live on Main Street and you live on 3rd Street, there's no ranking there. In other words, it's just a description of the street that you live on. So qualitative data are generally described by words or letters. Okay. Quantitative data, that's always numbers. Okay. These are the result of counting or measuring attributes of a population. For example, the amount of money you have in your checking account, your current pulse rate, how much you weigh, the number of people who live in your town, and the number of students who take statistics are examples of quantitative data. So quantitative data, it might be discrete or continuous. And I'll show you what the differences are here in the next slides. Discrete data, that is all the data that are the result of counting, are called quantitative discrete data. So these data take on only certain numerical values. If you count the number of phone calls you receive for each day of the week, for example, you might get values such as 0, 1, 2, 3, or more. Okay? Again, every day is probably different in that regard, or maybe. We start talking about continuous data. So all data that are the result of measuring are quantitative continuous data, assuming that we can measure accurately. So for example, if you and your friends carry backpacks with books in them to school, the number of books and the backpacks are discrete data. But the weights of those backpacks are continuous data. So for example, the length of your commute to school, for example, would be continuous data. The weight of a bunch of bananas would be continuous data. Okay, the amount of time it takes you to drive from your house to your work would be continuous data. And then numbers that don't have whole numbers, they're fractions of numbers, would also be continuous data, like 2.4, 7.5, 11.0, okay, or 11.10. So let's say I go to the supermarket and I purchase 3 cans of soup, 14 ounces of lentil, and 19 ounces of Italian wedding, 2 packages of nuts, 4 different kinds of vegetables, and 2 desserts, Cherry Garcia ice cream, and 2 pounds of 32 ounces of chocolate chip cookies. What we want to look at here is to figure out which are quantitative discrete, quantitative continuous, and qualitative. So the 3 cans of soup, the 2 packages of nuts, 4 kinds of vegetable, and 2 desserts are quantitative discrete because I can count them. I had 3 cans of soup. I had 2 packages of nuts, for example. I can count the number of cans of soup. The weights of the soup are continuous because you measure weights as precisely as possible. Okay. So for example, as you can see, while I have a total of 3 cans of soup, some of them weigh a different amount than others, and I can measure out how much exactly that they weigh. So that would be called continuous data. Okay. Now the types of soups, those are qualitative. Okay. For example, what do we have? We have like Italian wedding and tomato bisque. Those are they're just different types of soups. They're not ranked in like how tasty they are or anything like that. They're literally just this type of soup, that type of soup. We're describing what type of soup it is, or what type of vegetable it is, or dessert it is. So that would be qualitative because now they're categorical. Displaying data. To make data understood by the average person looking at it, we need to display it in some sort of format that makes it easier to understand what we're trying to present. Okay? So tables are a good way of organizing and displaying data. And for some people, they might want to see the information in a table, but realistically, graphs and charts become more helpful in understanding data. There aren't any strict rules concerning which graphs to use. Frankly, it's going to depend on what information is being presented and who your audience is. So 2 graphs that are used to display qualitative data are pie charts and bar charts, or bar graphs. Here's a pie chart. You'll see that I have 2 colleges represented here. And 2 categories of data. in this example. So in a pie chart, categories of data are represented by wedges in a circle, and they're proportional in size to the percent of individuals in each category. What you'll see here by looking at a pie chart is it's very easy to tell, looking at De Anza College, that over half of the students there are part-time. And at Foothill College, almost 3/4 of the students are part-time. Sometimes percentages add up to be more than 100% or less than 100%. In the graph below, the percentages add up to more than 100% because students can be in more than one category. You'll see here that we have 3 different categories. We have our full-time students, we have students who intend to transfer, and students under the age of 25. Now, those categories, they're quite different, okay, in terms of what they're looking at. It's not just a category of part-time students and full-time students, like we had in the previous example. So a pie chart wouldn't be a very good tool to use here because the categories are so disparate and they add up to more than 100%. So in this example, we typically will use a bar graph. A bar graph is appropriate to compare the relative size of these categories. For example, in this bar graph, you can see that all of our students are 100%, okay? But only 40% of them are full-time. However, 48.67% intends to transfer, and 61% of them are under the age of 25. So there are several pieces of information that are being shared in this bar graph. Also, pie charts cannot be used if the percentage is, once you have everything added up, the total percentage being represented must be 100% in a pie chart. If it's less or more, and you don't have another category called like other, you can't use a pie chart, okay? So the following pie charts have the other unknown category included since the percentages must add to 100%. Chart B, you can see chart A and chart B, we're both presenting the same information, okay? But typically in a pie chart, what we will do is go clockwise from the top, having the largest portions, categories being represented here, okay? Being in the largest, starting clockwise, going to our smallest percentages or categories here. For example, while it's easy to see in both pie charts that Asians and whites tend to make up the greatest ethnicity of students, you can also, on the pie chart on the left, isn't as clean, it isn't as clear as the pie chart on the right, because the pie chart on the right, again clockwise, goes from the greatest number to the smallest number and percentage-wise in the different categories. It's easier to tell, for example, that there are more black students than there are Filipino students at 5.8% versus 5.3%. Now, the thing is with bar graphs, they can be difficult to understand visually if they're not sorted, okay? The top bar graph here is not sorted. The bottom bar graph is sorted by size from the left to the right. Largest size on the left, smallest size on the right. You'll see that it's much easier to see at a glance that the largest percentage of ethnicity of students is Asian, and the smallest is Native American. When we're sampling is just gathering information about an entire population. Often it costs too much, or it's virtually impossible. Again, let's say our population is every household in the United States. Okay, it's going to be virtually impossible to reach out to every single one of those households and send them a survey and have them all fill it out. Okay, and to collect that data and process it to get to your results would be a daunting task, very time-consuming, very expensive. It's not really feasible. Okay, instead, we use a sample of the population. Now the sample should have the same characteristics as the population it is representing. Okay. For example, let's say I want to do research on Toyota owners. Toyota's an automotive manufacturer, so Toyota car owners. Okay. If my population is everybody that owns a Toyota, we're talking millions of people. So if I want to take a sample, I can say, okay, well, I'm going to sample 1,000 current owners of Toyota vehicles. Okay. That sample size should be ample to represent the overall population. It does have the same characteristics because it is you're reaching out to Toyota owners. I'm not reaching out to Ford owners if my population is Toyota owners. You want to use the same, just a sample of the overall population of whatever or whomever it is that you're studying. Okay, so most statisticians, they tend to use various methods of random sampling in an attempt to achieve the goal of setting up a good sample size. Simple random sampling is a straightforward method for selecting a random sample. Here we're going to give each member of the population a number, and then we'll use something like a random number generator to select a set of labels. These randomly selected labels identify the members of your sample. Any group of n individuals is equally likely to be chosen as any other group of n individuals if this simple random sampling technique is used. Each sample of the same size has an equal chance of being selected. So for example, suppose Lisa wants to form a 4-person study group from her pre-calculus class, which has 31 members. To choose a simple random sample of size 3 from the other members of her class, Lisa could put all 30 names in a hat, shake a hat, close her eyes, and pick out 3 names. A more technological way is for Lisa to first list the last names of the members of her class together with the 2-digit number, and then calculate using a random number generator to pick 3 times from the number between 1 and 30. Okay. Now let's say there are 731 students currently enrolled in statistics at your school, and you wish to perform a sample of 8 students to answer some survey questions. Here, you would select the students who will belong to the simple random sample using a random numbers table. And again, you can do this with software. I know you can do random numbers with Excel. There are also simple random number generators on the internet that you could go out to and plug in your range of numbers, and it'll print out a list of random numbers, and then you would use those to select your sample, for example. Now a stratified sample, what we're going to do here is we're going to divide the population into groups. We call those strata. Okay, so all you're doing is you are finding a way to break the population that you're looking to study out into different specific groups. So what you can do is stratify your college population, for example, by department, and then choose a proportionate simple random sample from each stratum to get a stratified random sample. So for example, let's say you have several different departments in your college. You might choose 5 of them. Doesn't matter what it is, like let's say English and math, science, business, and music, okay, for example. And you want to choose a sample of 50. All you would do is select people that are in those departments, and then you would pick 10 at random, 10 people in the departments to use as your sample size. Okay, that's what we call a stratified sample. Okay, now cluster samples are kind of like that, but they're a little bit different. To choose a cluster sample, all we need to do is divide our population into clusters. Okay, so let's say, for example, and then you would randomly select some of the clusters. So all the members from that cluster are in the cluster sample. So it's a little different than random sampling, where we're just kind of picking people from different clusters or different stratas. In clustering, we literally take the population and we chunk it off into so many people in these different clusters, and then we go and we select the cluster that whatever cluster is that we choose, the people that we're going to then sample the people within that cluster. Okay, so let's say I randomly sample 4 departments for my college population. The 4 departments make up the cluster sample. Then I divide my college faculty by department. Then the departments are the clusters. I number each department, and then I choose 4 different numbers using simple random sampling. All members of the 4 departments with those numbers then are the cluster sample. Another example that we might take with the cluster example is, let's say we have 100 people that we have in our population. We would take that population and maybe divide it by 3, so there are 3 different clusters. Let's say 2 of them have 33 each, and 1 of them has 34. We would randomly, take the cluster 1, cluster 2, cluster 3, write them down on a piece of paper, put them into a hat, reach in, and then pull out one of the pieces of paper, look at it, and that would give you a cluster name that you are going to survey, and then you would contact everybody within that cluster. A systematic example is where we randomly select a starting point and take every nth piece of data from the listing of a population. Okay, so how this works is, let's say you have to do a phone survey. Your phone book contains 20,000 residence listings. So your thing here is you're going to try to choose 400 names for the sample. You number the population 1 to 20,000, and then you use a simple random sample to pick a number that represents the first name in the sample. Okay, so let's say your number comes up at, so let's say number 100. Okay, then you choose every 50th name thereafter until you have a total of 400 names. Okay, now you might have to go back to the beginning of your phone list if, let's say your random number comes up at 19,900 or something like that. You're definitely going to have to go back through that list and then go through every 50th name to get to where you need to be and have all of your sampling. So systematic sampling is frequently chosen because it's a simple method. What we usually find in statistics is that the simpler it is to set up your sample and make sure that it's fairly randomized, it's more likely that whomever's doing those calculations or setting up these studies, we tend to try to keep it simple when possible. Now, convenience sampling is probably the most simple type of sampling you can do besides completely random sampling. And convenience sampling is not random, though. Convenience sampling is when you literally just have a population nearby, maybe physically or virtually, but it's just a real easy population and sample that it's very convenient. So, for example, let's say you work for Best Buy. Okay, and they are conducting a marketing study by interviewing potential customers who happen to be in the store browsing through available computer programs. So the results of the convenience study might be very good in some cases and highly biased in others. So for example, if somebody's coming into the store and they are looking at software, buying software, virtually going to the store, looking at the shelf and buying some software, they're probably going to be a different customer type than, say, somebody that goes on Amazon and looks for software or buys it directly from the company. Different type of shopper, potentially. And so there might be, if we're looking at characteristics of shoppers, it's definitely you're definitely going to have a different result by looking at one type of shopper versus another. And so convenience sampling can be somewhat biased in that regard. It's not random. Okay? Just something to keep in mind. Now, when we start talking about selection with sampling here, we have uh, with replacement or without replacement. So true random sampling is done with replacement. That means that once you have, if you're using like a random number generator, for example, and you're not telling the random number generator to remove the person from your list as you're running through and randomly going through the list of numbers and generating your list. Every time that person is picked, their ID basically is put back into the list and potentially could be picked again. Okay? That means that person might be chosen more than once. That's with replacement. Okay, so what we do here is it provides the opportunity for that person to be picked more than once, and that poses an issue. So typically, what we do with random sampling, okay, is we don't do truly random sampling, because that's what that would involve replacement. But we don't want to pick somebody twice. If we're picking out a sample size of, let's say, 100 people, we don't want 99 people that we've chosen, or well, 100 total, no, 99 total people, but have 100 responses. Okay, that's not good. That's not going to give you accurate results that you're looking for. You literally want 100 different people, okay, instead of 99 people, but one person has two results. They went in and filled out the same information because they were picked twice. Okay, practically speaking, that shouldn't happen. Okay, so what we usually do here is we usually do simple random sampling, and we do that without replacement. Okay. Surveys, those are almost always done without replacement. That is, a member of the population can only be chosen once. So most samples are taken from large populations, and that sample tends to be small in comparison to the population. For example, let's say you have voters in the United States, and you're trying to determine if they are going to vote for a Republican candidate or Democratic candidate. If we were to poll every voter in the United States, that's hundreds of millions of people. Okay, it would take forever. But what we can do instead is select maybe a few thousand people throughout the United States in different areas, in urban areas and rural areas, East Coast, West Coast, Midwest, and that would give us even with the smaller sample size, and overall it would be very similar in as far as the results to if we sampled the entire population. So if we have large population and we just need to be a smaller sample size, sampling without replacement is approximately the same as sampling with replacement, because the chance of picking the same individual more than once with replacement is very low. The whole thing here is that we tend to, when we're doing sampling, for the most part, we'll do it without replacement. Okay. You have different types of errors. Anytime you collect data, you're probably going to collect some data that is incomplete or has some sort of error. This happens. It's totally normal, and we deal with this by just being aware that there are sampling errors and non-sampling errors. The larger the study, the more samples you have, the larger the sample size, the more participants you have, the more responses you have, the more complex. Let's say it's, you're doing survey research, you're using a survey to perform your research. Your likelihood of having some sort of error is increased. So the two major types of errors are sampling errors and non-sampling errors. Okay. A defective counting device, for example, can cause a non-sampling error or technical glitch. Let's say your software, the formula that you created or whatever to calculate your or analyze your results was done incorrectly. Okay, that would be a non-sampling error. Or let's say you're tabulating votes in the presidential election and you have a machine that is defective. It can happen, does happen sometimes. That defective counting device would cause a non-sampling error. It could give you an invalid result. And it's not because the ballots that you were tabulating were incorrect. It's because it didn't tabulate them. It didn't count them correctly. It can happen, does happen. It happened in the presidential election of 2020 in a couple of cases. And so they had to go back and recount the ballots because of a defective counting machine. Happens. And so one thing to keep in mind when we look at sampling errors, the sampling error, it could be anything of just that there aren't enough, the sample's not large enough. For example, if I have less than 100 responses, that could lead to more sampling errors and incorrect information than let's say if I have 200 or 300 samples. I have send out a survey to 1,000 people and I get 200 of them back. Much more likely to be the correct information versus if I only get 20 back. Okay, and so we have to be careful about sampling errors. The more samples you have, the smaller the sample error. Okay, so for example, if I have 200 people that respond, much more likely to have good data than if I only have 20. And so we just need to be aware of that. Now, setting up, when you're setting up your research, what you might find is that you may have a requirement for how many responses you would get to a survey to where you'd be able to use that information. And if you don't reach that, you might have to increase your sample size, for example, and reach out to more people. Okay, that can happen. Non-sampling errors, if you have a defective device, like your computer's not working properly, or you have a formula that you don't have put in correctly and your calculations are off, then you would fix that error and then reanalyze your data. Okay. So this next slide talks about critical evaluation. Now, there are going to be issues with samples in studies and things like that in statistical analyses, the statistical studies that we need to be aware of. Okay, problems with samples. Again, your sample size needs to be representative of the population. Sample's not representative of the population, it's biased. Okay, and biased samples that aren't representative of the population give results that are inaccurate. Okay, or they're just completely invalid. So let's say, for example, I want to look at automotive people who own cars, and are they happy with their cars? Okay, and the population is everybody who owns a car, but I only pick people who own Toyotas. Okay, I am not. That is the sample size is not indicative of the population because there are multiple car brands out there. So I'm only getting the results back from Toyota owners. So basically I'm basing this entire study and all the results that I'm going to get, and whatever I'm writing up is the results of the study are based on people who own Toyotas and not people who just own cars in general. It's a poor study. The results are totally invalid. And if you're a researcher and you're looking at that, you would say, well, your study's not correct. You need to go back and redo it because your sample of your population is not a representative population as a whole. So self-selected samples, if these are only by people who choose to respond, such as call-in surveys where let's say you send out a survey and somebody has to call in or email their responses to you, and that's what your dependent upon, those can be somewhat unreliable. Your sample sizes, if samples are too small, they're definitely they might be unreliable because you're not, if you only have a few people responding, for example, to a survey, the accuracy of your data would be pretty questionable because you don't have enough of it. Larger samples are better. Okay. Sometimes you run into situations where you can only get to a small number of people. For example, people who have like rare medical conditions. There aren't that many of them, so your sample size is going to be small. Or the results of crashing, doing crash testing on cars. Okay, we're not going to crash every car in the United States to see how it fares out in a crash. We're going to take a very small sample of that because it's very expensive to do, to crash and purposely destroy a car to see how well it fares out in testing. The automotive manufacturers aren't going to provide you with a very large number of those cars. So, we're going to have a small number. That's just how it's going to be. Okay. Undue influence. Undue influence is where you collect data in a way that influences a response. Okay, so let's say you get a survey and it asks questions where it's like, so how much do you like butter? Isn't butter the best thing you've ever had? Or something like that. You might be influenced to say, oh yes, it is the best thing I've ever had. Or, oh, I really like this brand of butter because the way that they the survey is structured, they can, it makes it sound like you're almost as if they are influencing you to say that their brand that they're asking about is the best brand of butter, for example. It can influence your choices on your responses. And so we just need to make sure that when we're asking questions, we just ask the questions without bias if possible. Okay, non-responses, that's an issue. Let's say, for example, you're asking for somebody's ethnicity or their gender, and they refuse to answer, or they leave that information blank. If our study doesn't have the ability for somebody to say like a no response or prefer not to answer, if I only have the category and gender, for example, of male and female, that if somebody doesn't answer and I don't have that third category in there, I may not be able to use that response, for example, because it's incomplete. So that's something to be aware of when you're setting up a study, that you make sure that you ask questions and you give somebody the ability to not answer a certain component of that study if possible. Okay. The other thing too is that sometimes you have to watch with responses to surveys or to studies in general. When somebody has an overwhelmingly positive review, or for example, if you ask somebody's opinion on something and this just seems like they are overly positive or extremely negative, usually that person's biased in one way or another, and we might have to remove that result from our results or from our calculations because it is so biased one way or another. It's way out there in terms of it's not even remotely close to other responses in our survey, from our survey, and maybe we remove it. Okay, and if you remove that response, you need to indicate why. Okay, it can't just be because you didn't like what they said. It has to be like, okay, it's not representative even at all of comparison to what other responses were. Okay. And you'll know that when you go and if you do a survey and you start looking at the information coming in, it'll be like, wow, this thing's way out there. Yeah, I can't use that. Okay, causality. So we run into this a lot in statistics where people think that, okay, just because something happens, if there's a relationship between two variables, it means that one caused the other. That's not true. They might be correlated because of their relationship through a different variable potentially. Okay, so let's say we look at like overall reliability long-term reliability of cars. Okay, and it might be the more expensive a car is, the more reliable it's going to be. Okay, not necessarily true. Okay, it's not. There's not a direct link that the cause would be the more the car being $50,000, that it's going to be, the effect is that it's more reliable than a $30,000 car. Not totally true. There are other factors that go into the more expensive a car is, the more likely the person who owns it has the means to maintain the vehicle properly, and therefore it is more reliable, potentially. I mean, there are other factors as well, but that's one of them. Okay, so there's not a direct causation between the more expensive the car is and the more reliable it is, and that's something to keep in mind. Self-funded or self-interested studies. When when a company, you see this a lot in the nutritional supplement industry. A company will say, they'll come up with a product and they'll say, this study shows that our product, I don't know, makes you skinny or adds muscle or whatever it's supposed to do, whatever they say this product does. Okay. A lot of times when you look at these studies, they are actually funded by the company themselves. So when we look at studies that are funded by the company on the company's product, it does not necessarily mean that the results can't be trusted. You just need to understand that if the study is self-funded, it could potentially skew the results because the people who are carrying out the study are being paid by the company who creates the product. Okay. I'm not saying that everybody is dishonest, but there could be some dishonesty or pressure to have a positive result on the study. So for example, if the supplement manufacturer says, oh, this product increases muscle mass or whatever, people who take it and then work out, the scientists who are doing the study might feel pressured to look at, how much is this is how well does the supplement work. They feel kind of pressured sometimes to come up with results that might be favorable to the supplement company. Not always, but sometimes that does happen, and you need to be aware of it. Okay. Misleading use of data, using like improperly displayed graphs, incomplete data, or lack of context. This is a lot in, especially when it comes to politics. A lot of times we will see that we can use certain types of data or data that isn't totally cleaned up. You actually saw this in the 2020 presidential election, where there was missing data. There was data that just hadn't been fully tabulated yet, and it caused a lot of, or data that was in there without context with some of the counties in certain states, and it caused a lot of confusion. And actually, I believe, and it's the assessment of people who look at statistics and in general, is that without complete information and context for where information comes from, it can be confusing, especially to people who don't know a lot about statistics. And a lot of that was used in the 2020 election, or at least afterwards, in the controversy surrounding the ballot counting. And that's just an example of what can happen when we have a misleading use of data. It can sow a lot of confusion, and it can also provide bad information. And so, that is something that unfortunately spurred a lot of controversy that will probably persist for years, where there were definitely some counting issues and some statistical discrepancies in certain, probably in every state, but the only states that were really looked at were the swing states, or states that could have an impact where the presidential race was close for one candidate or the other. And under that level of scrutiny, what we're looking at is there was incomplete data that was crunched, and analysis done on data that wasn't complete, or data that some of it, frankly, at the time had some issues that they had to go back and rectify. For example, tabulation machines that were breaking and things like that. So we have to be very careful about our use of statistics because, again, they can be used to mislead or misrepresent. And it does happen, and you'll see that in politics. I don't know about the rest of the world, but in the United States, on the national level, you certainly do see where statistics can be used in a way to try to sway your position one way or another politically. And it's unfortunate that happens, but it does happen. And then the last one here is confounding, and that's the effect when multiple factors on a response cannot be separated. This just makes it difficult to draw valid conclusions about the effect of each factor. So, for example, if you get a vaccine or something like that, or use a certain sort of medication, let's say it's you're taking a medication for cholesterol or something like that, but it also affects several other systems in your body, and it's really difficult to determine what the overall impact is on that drug on a certain area when it's also affecting these other areas, which can cause other problems with, say, your cholesterol level. It can be complicated and very difficult to go in and actually separate out and get down to cause and effect because you have all these different variables in play, and that can be the more complex your statistical analysis is and what you're studying can lead to more confounding. So yeah, it's a problem. So if we take a look here and we say a study's done to determine the average tuition that San Jose undergraduate students pay per semester, each student in the following samples is asked how much tuition he or she has paid for the fall semester. And we want to look at what is the type of sampling in each case. So for example, the first one, if we sample 100 undergraduate students, is taken by the organizing the students' names by classification. Okay, what would that be? We can see that the top A, that's stratified. Again, we're taking our sample, and we are separating it into, looks like 4 different categories. Okay, 4 different strata, and then we're selecting 25 students from each. So that gives us 100. Okay, B is when we use a random number generator, and then we get whatever the first one is with the random number generator, and then every 50th student we're chosen until we get 75 students included in the sample. Okay, that's systematic. That's what that one is. And then the third one is where we literally just randomly select 75 students out of the population. Okay, it's just a random sampling, simple random. The fourth one here, D, is where we give each category here, each cluster, if you will, a number. Okay, based on what year they are in college, 1, 2, and 3, and 4 for freshman, sophomore, junior, senior. A random number generator is used to pick 2 of those years, and then all students in those 2 years are the sample. That's a cluster. That's a very traditional cluster. Literally, I just segment out my population, and then I go and I pick a cluster or 2, and that's my sample size. That's the simplest cluster there is, probably. And then the last one here is where your administrative assistant's asked to stand in front of the library one Wednesday to ask the first 100 undergraduate students he encounters what they paid for tuition. That is a convenience cluster. Or I'm sorry, convenience sample, not cluster. Read that incorrectly. Convenience sample. It's where we just hound people as they're coming in the door. Literally. And at college, you'll see that the convenience sampling is very popular when it comes to surveys. Okay, now let's start talking about variation. Variation is present in any set of data. Okay, chances are of you, let's say, running a survey twice and having the exact same results is very unlikely. Okay, so for example, 16-ounce cans of beverage may contain more or less than 16 ounces of liquid. It's never going to be absolutely perfect. You might have a little bit more than 16, you might have a little bit less. Okay? But on average, the goal is to have them to about 16 ounces. Okay. Now, when we start measuring out, let's say, for example, a 6-pack of Mott's applesauce, apple juice, you're going to have, maybe one of them that's right on 16, if even that. But in general, it's a little bit more, a little bit less, as we can see here, that it ranges anywhere between 15 or 14.8 and 16.1. Okay. So measurements of the amount of beverage in a 16-ounce can may vary because different people make the measurements, or because the exact amount, 16 ounces of liquid, was not put into the cans. Manufacturers regularly run tests to determine if the amount of beverages in a 16-ounce can falls within the desired range. Again, there's always going to be some variation, but our goal is to get as close to 16 as we can. But there's a tolerance on one side or the other that's acceptable. What would that be? It depends on the manufacturer, for example, and what they deduce. Maybe Mott's is okay with having 15 to 17. I mean, I don't know. You'd have to ask Mott's. All right. Let's take a look at frequency tables, and levels of measurement. So, in statistics, at some point we usually round off numbers. The simplest way to round off your answers is to carry your final answer one more decimal place than was present in the original data. When we do when we round, though, we only round off on our final answer. So, for example, let's say on our previous slide, we had a 6-pack of the Mott's apple juice, and we had like 14.8, 15.8, 16.1. I mean, all these different, but you can see that that number was just the number of ounces, 14.8 ounces. What we wouldn't do is we wouldn't round off that number to say 15 until before we do the calculations, because then it can seriously make our final number, after all the calculations are done. Let's say we want the average of those cans. It's going to be way off if we round before we calculate. You only round after you're done with your calculations. Whatever your final answer is, that's when you round. Do not round off anything at the beginning. Don't round off anything with intermediate results. Now, let's say, for example, you have a number like pi that just carries on forever. That's unlikely to happen. But if it does become necessary, what you would do is you would get to at least 2 decimal places after, twice as many decimal places as your final answer. Okay, if you encounter a number that runs on forever. Now, in this class, you're going to be using a computer for your calculations, or calculator if you have one, but it's not required. You're not going to sit down and calculate the stuff out by hand. So chances are you're not going to have a number anyways that's going to go on forever like pi does. So you don't have to worry about this. Okay. When you get to your final answer, though, then feel free to round it. You can even have Excel round it or JASP round it if you want to. Okay. So it's not really necessary to reduce anything in the course, especially probability. It's if you have a fraction or decimal places out a few points, that's fine. That's what we would expect. So you're not even gonna have to worry about rounding it off anyways that much. It's just, like I said, when we round in stats, we don't do it until the very end. Otherwise, it throws off all of our results, and we don't want that. We want our results to be as accurate as possible. Okay, there are different types or different levels of measurement. Okay, what measurement means is it's the way that our set of data is measured. Okay, it's called our level of measurement, and correct statistical procedures depend on a researcher being familiar with these levels of measurement. Not every statistical operation can be used with every set of data. So data can be classified into 4 levels of measurement. And we have 4 different types, or 4 different levels, and they are from the lowest to highest level. Okay, so it's important to know what the levels are and what the ranking is and how they should be used. You have nominal, ordinal, interval, and ratio scale levels. Your nominal scale, this is data that is measured using a nominal scale, is qualitative. Okay, think of categories, descriptions. It is not arranged in any kind of order. It doesn't have any kind of like numerical importance. For example, if it's nominal, that's stuff like colors, names, labels, and favorite foods, along with yes or no responses. Those are examples of nominal level data. Now, nominal scale data, it's not ordered. Okay. For example, if I'm trying to order people according to their favorite food, under most circumstances, that doesn't make any sense. Putting veggie pizza first and vegan sushi second is not meaningful. So, for example, let's say I like to pick on cars. Something I'm kind of familiar with, and it's kind of a hobby of mine to look at the automotive industry. If I'm looking at nominal data, nominal scale, that would be like, well, what make of car do you drive? Do you drive a Ford or a Ferrari? Really, does it really matter how those are ordered? For most cases, no. It's just literally a category. It's just descriptive information. Okay, so that's nominal scale stuff. That's what you would put in the nominal scale. Your ordinal scale can be ordered. Okay, so that's the big difference between that and nominal scale. Nominal scale is literally just like, it's just a description. Okay, ordinal scale is different. That's data that's measured using a nominal scale, but it can be ordered. So for example, ordinal scale data is a list, for example, could be the list of the top 5 national parks in the United States. The top 5 national parks in the United States can be ranked from 1 to 5, but we cannot measure differences between the data. Okay, so that's ordinal scale. Interval scale is data that is measured, that's similar to ordinal level, but because it has a definite ordering, but there's a difference between the data. So for example, temperature scales like Celsius and Fahrenheit are like the top things, the easiest things to think of, where we use the interval scale. In both temperature measurements, 40 degrees is equal to 100 minus 60, okay? The differences make sense. The higher the number, from 0 to 100 or whatever, the hotter the temperature is. But 0 degrees does not, because in both scales, 0 is not the absolute lowest temperature. Temperatures like 10 degrees Fahrenheit and negative 15 exist and are colder than 0. So these two scales, or the two temperature scales, measure the same thing. They measure temperature. They just have a different range. Okay. You have they start at different feelings of the temperature, basically, and so Fahrenheit, if freezing is 0, I'm sorry, 30 degrees or 32, and Celsius is 0. Okay, so the scales are different in terms of the temperature that they record, I guess, sort of. They just use 2 different scales to measure the same thing. Okay. Ratio scales, that's data that's measured using the ratio scales, takes care of the ratio problem and gives you the most information. So ratio scale data is like an interval scale data, but it has a 0 point and ratios can be calculated. What does this mean? It just means, for example, like for multiple choice statistics, final exam scores are 80, 68, 20, and 92. Okay. What does that mean on its own? Nothing. Okay. Because we don't have anything at that point to compare them to. However, once we say that we have 100 possible points, now we can rank them, okay, these scores, because they're all scores that 80, 68, 20, and 92 are now out of the possible 100, which is the maximum value. Okay. The exams are, let's say they're machine graded. The data can be put in order from lowest to highest. So for example, the person with the 20 has the lowest score. The person with 92 has the highest score. Okay. So the differences between these data, they have meanings. The score 92 is more than the score of 68 by 24 points. Ratios can be calculated. The small score is 0. So 80 is 4 times 20. The score of 80 is 4 times better than the score of 20, for example. And the person with 92 got 92% of the available points. They did very well. The person with 20, not so well. Okay, probably need to go visit the learning center. Frequency and frequency table. So 20 students were asked how many hours they worked per day. Their responses in hours are as follows. And it gives you several different hours that the students have worked per day, ranging between 7 hours and 2 hours, it looks like. Okay, so this table lists the different data values in ascending order and their frequencies. What's important here is that your data values and your frequencies match. So for example, there are 3 people who said that they worked for 2 hours per day. Okay, at the top there. At the bottom, you have 1 person who said that they worked 7 hours per day, which actually is that's quite the haul for college to be able to work that much. But anyways, your data values and your frequencies need to match. In this case, we've listed those values in ascending order. That doesn't matter as much. It can be ascending or descending. It depends on what makes sense from what you're trying to display. Okay, so here's our frequency and frequency table. You can see here, we can even do a relative frequency. So for example, if you have, it's the ratio, the fraction or proportion of number of times the value of the data occurs in the set of all outcomes to the total number of outcomes. So to find the relative frequencies, you divide each frequency by the total number of students in the sample, in this case 20. Relative frequencies can be written as fractions, percents, or decimals. So if I have 20 students and the frequency is 3, then my relative frequency is 0.15, okay? And that's what you would get if you just calculated it. It would tell you 3 divided by 20 is 0.15, okay? Typically, if we're going to round this relative frequency, you do it 2 decimal points out. So 0.15, so let's say it's 0.149, you would say 0.15. Your cumulative relative frequency is the accumulation of the previous relative frequencies. So if I'm going to find this cumulative relative frequency, all I do is I add all the previous relative frequencies to the relative frequency for the current row, and then you add. Basically, so let's say your first frequency is 0.15 and your second frequency is 0.25, then you would end, you would take both of those and say 0.4, and then you keep repeating and repeating. So 0.4 plus 0.15, and then that's 0.55, and then you add that to the next row, and so on and so forth until you get down to the bottom. The last entry of the cumulative frequency column should be 1, indicating that 100% of the data has been accumulated. If it's not 1, usually that means that there's an issue with your calculation. You need to go back and change that. So we can say that 95% of our people, work less than or right at 6 or fewer hours per day. Okay, because there's only 1 person or 5% that works 7 hours per day, which kind of stinks if you're going to college. That's a lot of time to log in a day. Okay, so here's just an example. It represents the heights in inches of a sample of 100 male semi-professional soccer players. And you can see that 99% of soccer players are at or below 73.95 inches tall. There are very few of soccer players that are like super tall, I guess, in this sample. All right, talk about experiments and ethics real quick. So uh, experiments are when we're trying to find an answer to something. Okay, so for example, does aspirin reduce the risk of heart attacks? Is one brand of fertilizer more effective at growing roses than another? Is fatigue as dangerous to a driver as the influence of alcohol? Questions like this are answered using randomized experiments. So there are important aspects, for example, of experimental design. We want to make sure that at the end, well, two things. One, we get reliable and accurate data, and then also that we are, when we're working with subjects like humans or animals, that we do it safely, okay, and ethically. So the purpose of an experiment is to investigate the relationship between two variables when one variable causes change in another. We call the first variable the explanatory variable. The affected variable is called the response variable. So in a randomized experience, the researcher manipulates values of the explanatory variable and measures the resulting changes in the response variable. The different values of the explanatory variable are called treatments, and an experimental unit is a single object or individual to be measured. Okay. So for example, researchers want to investigate whether taking aspirin regularly reduces the risk of a heart attack. 400 men between the ages of 50 and 84 are recruited as participants. The men are divided randomly into two groups. One group will take aspirin, and the other group will take a placebo. Okay, so you have two groups. One gets aspirin, one gets placebo. It's just a sugar pill, basically. It's a pill that has nothing in it. Each man takes one pill each day for 3 years, but he doesn't know whether he is taking an aspirin or a placebo. At the end of the study, researchers count the number of men in each group who have had heart attacks. Okay? So there's a lot to unpack there, and we need to know like what the different terms are. The population that we're looking at studying here are men aged 50 to 84. Now the sample size, again, it's going to be impossible for us to pull every 50 to 84-year-old man in the United States, for example, and have them do this experiment. It's just not possible. So we pick a random sample of 400 men. Okay. Easier to do. Still, it's not a large study, but still a decent sized study with 400 people. The experimental units, those are the guys in the study. Okay. The explanatory variable is the oral medication. Okay. The treatments, remember there were two treatments. You had half of the guys getting aspirin and the other half were getting sugar pill or placebo. Okay. It doesn't do anything directly. The placebo doesn't do anything directly to treat the heart disease. The aspirin does. Okay, and then the response variable was whether the subject had a heart attack. And so, what we're looking at doing here is we're going to find out if well, hopefully that's the goal here of this experiment, is to find out if aspirin had any effect on the rate of heart attack. And so we're going to compare the results from the placebo and the results from people who got the aspirin to see which group fared better, I guess. Okay, now, another thing we have to look at is ethics when we're doing research. Now, in business research, ethics are, well, just in general, ethics are pretty critical. But ethics are designed to protect people and animals from, in general anyways, from harm. Okay. What we want to do is you want to make sure that, for example, if you're doing a study on any human subjects, that you are making it as safe as possible, that you're protecting their identity if that's an issue. So all kinds of stuff that goes into ethics. Okay, the big overarching thing here is that you want to make sure that you are being lawful and you're not doing something that's illegal. Like you can't run around and inject people with a drug and not tell them what all the potential side effects might be when you're testing this thing. You have to be you have to behave ethically and legally. For example, if we're studying college students, let's say you want to test out some, I don't know, maybe you're making some new soft drink or something like that, and you're saying, hey, try this soft drink. Tell me how it tastes or whatever. You would need to disclose what's in the soft drink, for example, as part of it. You would need to do that. You couldn't just say, oh yeah, well it's secret. I can't tell you what's in it. You need to make sure that they know. You can't put people at undue risk. So, for example, you couldn't. I don't know. Let's say you're a firearms manufacturer and you want to come up with a new design or whatever. Before you have somebody fire that, you would want to make sure that you've done everything you can to make those experiments as safe as possible, so it doesn't blow up in their face. Anyways, those are just some ethical and legal ramifications we have to look at. And the Center for Disease Control and U.S. Department of Health and Human Services, they actually have training available for you to make sure that you're acting ethically and legally. So again, you need to reduce or minimize the risk to participants. And so, for example, if you have a drug that you are testing, and yes, it might help with heart disease, but there's a good chance it's going to give you a stroke. The risks might outweigh the benefits of testing that drug, and you may not even get into human trials with it, for example. And that's a real risk that these drug manufacturers make, is like, okay, well, we have this drug and it's going to do these wonderful things, but it's also going to kill 30% of the people who take it. That drug probably won't make it into into use for human use. I seriously doubt it. And so again, we need to minimize that risk. You have to give informed consent. It means the risks of participation, they need to be clearly explained to people. For example, if you're going to try out a new diabetes drug, you would need to make sure that people understand that the risk that they're taking is that this drug may not work like it's supposed to, and they could exacerbate their diabetes or worse. Again, they need to know these things. They must consent in writing, and the researchers are required to keep documentation of that consent throughout the study and afterwards too. And any data collected from individuals, you need to protect their privacy, their identity.